Welcome back again. Yesterday we saw the definition of congruences and some of its immediate properties, and we have seen these results stated in Theorem 4.2 also. But today we are going to prove this. Yesterday we could not prove this. So what do we mean by congruence? We say that a congruence is nothing but in one sense you can say that they are equivalent in some sense. Okay, A is congruent to A is congruent to B is congruent to uh, A is congruent to B is congruent to C, and then C is congruent to C. So that's what these are the things here in the first three results. They are they have been written. Okay. So we say that an integer A is congruent to B modulo n if and only if n divides A minus B. And as a result of this, it means that if n divides A minus B, it means that A minus B equals to some k times n for some integer k. And when we see that when A minus B is divided by n, it means n also divides B minus A. So it means that if A is congruent to B, then we can also say that B is congruent. Say in mathematics as symmetry. Okay. So if you see the the properties A, B, C, the first one is reflective. It shows the reflexive property. And the second one, it says that if A is congruent to B, and then B is also congruent to A. It means if we are taking this congruence as an equivalence, as an relation, okay, as an relation, this relation, the relation is nothing but when we say that A is congruent to B, it means that the relation is that n divides A minus B, that's all. And in other way, we can say that we can denote them by this relation, this divisibility condition, or else we can say that this thing we are representing that A is related to B if and only if A is congruent to B modulo n, like this. Okay. So the first one is reflexive. Second one says that if A is congruent to B, then B is congruent to A. Okay. And then third one is A is congruent to B and B is congruent to C, then A is congruent to C. So this is transitivity. So first three makes this congruence relation as an equivalence relation, and therefore it partition the set. Okay, under consideration. Anyway, so this was the information how we can relate them, these first three properties to an equivalence relation. Okay, and then the D part says that if A is congruent to B and C is congruent to D, then we can sum them side by side. That is, we can add A and C and B and D. So A plus C is congruent to B plus D modulo n. And then another implication of this is that we can multiply them too. So if A is congruent to B and C is congruent to D, then we can write A times C is congruent to B times D modulo n. So summation, that is sum and product side by side are implied. Okay, if we have two congruences. And then in E part, it says that if A is congruent to B, then we can add some another number like A plus C is congruent to B plus C. So we can add some fixed number here on both sides without changing without changing the result. Result, I mean, it means to, I mean to say that without disturbing the equivalence. okay, or without disturbing the congruence. Here also, if we can also multiply, we can also multiply. And then in F, we have if A is congruent to B modulo N, then A to the power K is congruent to B to the power K modulo N for any positive integer K. Okay. So if we have this one, this congruence relation, so we can say that K copies of A is congruent to K copies of B. So these are the meaning of the results. Okay. So let us see the proof one by one. And today we will be discussing more on these properties. Let us finish the proof of this theorem, and after that we can talk about some more properties of congruence. Okay. So first one, the first part, let us see. For any integer A, we have A minus A is equals to 0 times n. We can write like this, okay? And this implies that A is congruent to A modulo n. This is a very simple thing, okay? All right, and then the second one, let us see, second one, the part B. B says that if A is congruent to B, then B is congruent to A. Okay. So let us assume that let A is congruent to B modulo n. Then A minus B equals to some K times n for some integer K belongs to some integer K. Okay. Then we can write it B minus A equals to minus K times n, minus K times n for some K belongs to Z. And this implies that n also divides B minus A. Okay. And this means that B is congruent to A modulo n. Let us see this C part, that is transitivity part. So we have been given let A is congruent to B modulo n, and B is congruent to C modulo n. Then we can write. A minus B equals to some K1 times n. A minus B is equals to some K1 times n, and B minus C is equals to some K2 times n for some K1, K2 belongs to Z. Okay. To prove that A is congruent to C, we need to prove that A minus C. We need to prove that A minus C is divisible by n. So what we can do with the help of these two, we can add them side by side. So A minus B plus B minus C. In fact, this A minus C is equals to, we can write like this, A minus C is equals to A plus B and B minus C. And this is nothing but in the right hand side we have a K1 n plus K2 n, and we can take n common. So K1 plus K2 being integers, K1 and K2, their sum is also going to be an integer, and so K1 plus K2 times n. This implies that A minus B is equals to K1 plus K2 times n. And because K1 plus K2 is again an integer, sorry, this should be C, okay, not B. So it means that n divides A minus C. and therefore A is congruent to C modulo N. So this the C part we have established. The D part says that if A is congruent to B and C is congruent to D, then we can add them and multiply them side by side. Okay. So the D part, let A is congruent to B modulo N, and C is congruent to D modulo N. Then there exists K1, K2, the integers, such that A minus B equals to K1 times N and C minus D equals to K2 times N. Okay. So we need to show that we can sum them. That is, we need to find out A plus C. We need to find out A plus C. So what we can do? We can, I guess we can find out A from here and C from here. All right. And then add them. Okay. So for this, let us sum them. A minus C and A minus C. No, A minus B. A minus B plus C minus D, and this is equals to K1N plus K2N. And this implies that A plus C minus B plus D, this is equals to K1 times K1 plus K2 times N. Okay. Like this we can write. And therefore, this implies that A plus C is divided by B plus D. Okay. That is N A plus C minus B plus D divided by N. So N divides A plus C minus B plus D. This quantity. And this implies that A plus C is congruent to B plus D modulo N. Okay. I think this was what we were supposed to prove. A plus C is congruent to B plus D modulo. Okay. So next part is that we can multiply them side by side. Okay. And also we can write A equals to, if you see from here, A equals to, we can write K1 plus N plus B. Okay. K1 times M plus B. So we can write B plus K1 times N. And then C is equals to, I think, D plus K2 times N. Okay. So let us multiply them side by side. So A times C equals to B K1 times N, and then D plus K2 times N, and then we can multiply them. So we have a BD plus usual multiplication rule we follow. So B times D, and then we have K2 BD plus K1 Kn. We write we multiply this one. So Bn, we have Bn, not BD. We have Bn here. So K2 and B times N, and once we multiply these two, so we have K1 times D times N, and plus there is one more term, which is K1 and K2 times N square. So this is equals to BD plus, we can take N common from these last three terms. So we can take N outside bracket. We can write K2B plus K1D plus K1 K2 times N. Okay. So this means what? this means that AC minus BD is equals to K2B plus K1D plus K1 K2 n times n. So this implies that n divides AC minus BD. Okay. So because K1 and K2 were some integers and therefore they exist. So they are product and there are some, they also exist. Okay. And this implies that AEC is congruent to BD modulo n. Okay. So next part, let us see what is E, part E. A is congruent to B modulo n, then we can add some element on both sides and we can multiply also. Okay. So sum and multiplication, if you sum some fixed number on both sides, then this doesn't change the congruence. Okay. So let us see. Let A is congruent to B modulo n. It has been given. Then there exists an integer k belongs to Z such that A minus B equals to k times n. So this is what we know. Fine. What we can do? We can find out A in terms of B and Bk and n. So B plus k times n. Now we can add A plus C is equals to B plus C and this plus k times n. This implies that A plus C minus B plus C is equal to k times n. And this implies that n divides A plus C minus B plus C. All right. And therefore A plus C is congruent to B plus C modulo n. Okay. Now what else is there? We need to see if the same congruence is valid if you multiply with some fixed number on both sides. Also, from here we can A is equals to B times B plus k times n. Then multiply both sides by C. So we have A times C equals to B plus kn and then times C. And then the right hand side we have BC plus k times C k times n like this. And this implies that AC minus BC equals to some CK n. Okay. So this implies that n divides AC minus BC. Okay. And therefore AC is congruent to BC modulo n. Okay. So this proves the E part. And then the last part is that if A is congruent to B, then k copies of A is congruent to k copies of B modulo n for any positive integer k. So let us see let A is congruent to B modulo n. Okay, then we need to prove. K copies of A is congruent to k copies of B modulo n like this. So he used the principle of mathematical induction. We are not going to use the strong method, the strong principle of mathematical induction, but the simple one. So for k equals to 1, the result is true. result is true, as when we substitute here k equals to 1, k equals to 1, then we get this one, and of course this is a assumption, so obviously this is true. Now we suppose that the result is true for k equals to some L. Okay, then we claim the result is, then we claim, or we can write like this, then we claim a to the power L plus 1 is congruent to b to the power L plus 1 modulo n, like this. Okay. Okay, fine. So since by assumption is congruent to b modulo n, and e to the power L is congruent to b to the power L modulo n. Just now we have seen in case what is let me show you the part, I think D part, that we can multiply two congruences side by side. Okay, so let us multiply them side by side. So this implies that a times a to the power L is congruent to b times b to the power L modulo n. And therefore a to the power L plus 1 is congruent to b to the power L plus 1 modulo n. Okay, so by the principle of mathematical induction, the result follows. Okay, so we have proved these properties, and they are really very useful when you are computing congruence model of some numbers. Okay, and of course they are also going to useful in finding the remainder and all, so many things you can. Okay, here we have seen that we multiply them in these things are okay, but in D we have seen that we can multiply them and add side by side. The question is that can we subtract or can we cancel out? Okay, so here in part E we have seen that if A is congruent to B modulo n, then A times C equals to congruent to B times C modulo n. So the question is that is converse also true? So we'll see. When you'll see that in general it is not true, but under certain condition it is true, and that condition we will know in the next in the forthcoming results. Okay. So before going further, let us have some examples related to these, how we can use them. Okay. There is one result that is or we can find the remainder when or like this. Find the remainder when 2 to the power 20 minus 1 divided by 41. Okay, so very first stage it looks like difficult if we follow the usual procedure. This method is very convenient for this. So 2 is always a congruent to 2 modulo 41. There is absolutely no problem. Okay. And also 2 to the power 4 is congruent to 4 modulo 41. Similarly, 2 to the power 5 is congruent to 32 modulo 41. And both sides are same. You know that A is congruent to A modulo N. That is a reflection. Okay. So from here, it is 32. This 32 we can write. This 32 we can write. That is 2 to the power 5. We can write this minus 9 modulo 41. You know that 32 is congruent to minus 9 modulo 41. You know why? Because 41 divides 32, and this will come when this will come to the left. So we will have like this. Okay. So 41 divided by 32 plus 9, that is 41. This is true. Okay. So we can write like this. Reduce to it is relatively to find the square or cube of 9. Then to finding the square or cube of 32. Okay. So 2 to the power 5, and we can have a power of this as let us say 2. Okay, so we are moving towards this to get 2 to the power 20 first. Okay, so this will make a 2 to the power 10, 2 to the power 10. Okay, 2 to the power 10 and minus 9 square modulo 4. And this is we can do because you know that the last one, this property, okay, the property F allows us to take the integer integral power. If it is congruent to B, then we can write A to the power k is congruent to B to the power k modulo n, where k is an natural number. K is a natural number. Okay. So here 81, we have a 2 to the power 10 is congruent to we can write 9 square, that is 81 modulo 41. And because 41 is bigger than 81 is bigger than 41. Okay, so we can divide it this we can divide it. Okay, but this also it's a little bigger number, so we can write this 81 as minus 1 modulo 41 like this. Okay, so this becomes easy now. We can write minus 1 modulo 41. Minus 1 modulo 41. So now it is easy. 2 to the power 10 is congruent to minus 1 modulo 41 like this. So let us square again. So 2 to the power 10 and then square it. So this equals to minus 1 square modulo 41. Modulo 41. So this is a 2 to the power 20 is congruent to 1 modulo 41. So it means what? 41 divides 2 to the power 2 minus 20 to the power 20 minus 1. It means if 41 is dividing 2 to the power 20 minus 1, it means there is no zero, no remainder. Okay. There is no remainder. Fine. Any doubt in this as of now?
No, sir.
Okay, so remainder is what? Remainder is 0 in this case. Let us see in another example. Find the remainder. Here remainder is 0. Find the remainder when 1 factorial plus 2 factorial plus 3 factorial plus 4 plus 5 factorial, and so on, up to, for example, 100, or we can write thousands, 1000 also, 1000 factorial. Okay, you can change them. You can take different expression for this also. Okay, when this divided by 12, for example, we are considering that this is divided by 12. So what is the remainder? So how to proceed? We see that 12. Yeah, here no 12 is there. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. In 4 factorial, we have 4 times 3 times 2 times 1. Okay, so here we have 12 times 2 times 1, 4 factorial equals to. Okay, so this, and also in 5 factorial, we have a 5 times 4 factorial. In 4 factorial, we have 12 already. Okay, so in 6 factorial also, we have a 6 times 5 times 4 times 4 factorial, like this. So here also we will be getting 12. So if we continue and we observe that in 100 factorial also there is 12. So in each term from starting from 4 factorial until 100 factorial, we can take 12 common, and when we are dividing them by 12, we will be getting the remainder 0. Okay, we will be getting the remainder 0. All right. So therefore, the remainder is going, we are going to get will be 1 factorial plus 2 factorial plus 3 factorial, that is 6 plus 2 plus 1, that is 9. All right, like this. So we can write, since 4 factorial is equal to 24 congruent to 0 modulo 12, like this. Okay, and thus for we are reducing it under modulo 12. Okay, so thus for a k is greater than or equals to 4, k is greater than or equals to 4, we have a k factorial equals to 4 factorial times 5 times 6 dot 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 up to k. Okay, this is k, and this is congruent to 0 modulo 12 when we reduce it to modulo 12. Okay, so rest everything from starting from 4 factorial until 100 factorial will become 0. So the remainder is, therefore, so the remainder is thus all terms in the above series beyond 3 factorial are divisible by 12, and hence the remainder is 1 factorial plus 2 factorial plus 3 factorial, and this is equals to 1 plus 2 plus 6. This is equals to 9. Okay, so remainder is 9. Similarly, if you suppose, for example, if you are writing like this, suppose we are writing 2 factorial plus 3 factorial, or else you can take like this 5 factorial plus 6 factorial plus 7 factorial, and so on, and plus then up to 1000 factorial, suppose, or 10,000 factorial, and you can find out that if it is divisible by, for example, 30, okay, if it is divisible by 30, then what would be the remainder? Okay, remainder when divided by 30. Okay, so you know that in a 5 factorial you have 5 factorial, you have what? 5 times 4 times 3 times 2 times 1. So is there 30? 30 is there, or this is divisible by 30? The question is that. So you see 5 is there and 3 times 2 is there, 2 and yeah, 3 times 2 is there. So 5 times 6 times 4, here 30 is there, and times 4, that is we are going to get 120. Yeah. And certainly 120 is divisible by 30. So what would be the remainder when this expression is divided by 30? Hello.
Yes, sir.
Hello. Remainder क्या होगा? 30 से divide करेंगे इसको तो. I don't know whether you are listening the class or not. 0, yeah. 0. 0. Okay. So let us see some more results. Let us see some more results so that cancellation law always not allowed in congruences. Cancellation rule or law is not allowed in congruences in general. Okay, in general we cannot cancel. So for example, we can write 2 times 4 is congruent to 2 times 1 modulo 6. Okay, you know, in the left side we have 8, and in the right side we have 2, and 6 divided 6, 8 times 8 minus 2. But if he try to cancel these 2, so he will get a 4 is congruent to 1 modulo 6. Okay, so cancellation law is not allowed here. Okay, but under certain condition, cancellation law allowed. Okay, under certain conditions, cancellation can be done. Okay, so what is that condition? Condition is written in the next theorem. So this theorem says that if CA congruent to CB modulo n, CA is congruent to CB modulo n, then A is congruent to B modulo n by D. It's congruent to B modulo n by D, where D is the greatest common divisor of C and N. So let us see the proof. Okay, given that CA is congruent to CB modulo n. Then n divides, then this implies that n divides Ca minus Cv. Okay, because of what is called the definition of congruence. Okay, and there exists uh, integer k such that Ca minus Cb equals to some k times n, like this. Okay, Ca minus Cb equals to k times n. Okay. Now, since D is the greatest common divisor of Cn, so there exist R and S, they are integers such that now D is greatest common divisor, so D should divide C and as well as N also. So C equals to some D R and C equals to dr and n equals to ds. N equals to ds with R and S are relatively prime. R and S are relatively prime. Okay, so from here, this part, this gives us, we can take C common from here. So A minus B equals to K times N. And in place of C, we can substitute dr. Here A minus B is equals to K times N, and K, let us keep K as it is, and then here ds. So dd gets cancelled. So we have R A minus B is equals to K times S, is equals to K times S. Okay. Now, because S and R are relatively prime, these two are relatively prime, and therefore this S, S and R are relatively prime. So therefore S should divide, this implies that S should divide A minus B. This is because greatest common divisor of S and R equals to 1. They are relatively prime. Okay. We are using Euclidean criteria for divisibility. Okay. And then this implies that A minus B is congruent to 0 modulo S. Fine. If S divides A minus B, so A minus B is congruent to 0 modulo S, or we can write A is congruent to B modulo S, and that is A is congruent to B modulo. And what is S there? S from here we can compute. S is nothing but n by d. S is nothing but n by d. Fine. So if D is the greatest common divisor of C and N, this one, okay, which is the common on both sides of congruence, then we can write A is congruent to B modulo n by d. And when we can cancel exactly, if C and N are relatively prime, then D becomes 1. And in that case, we can write A is congruent to B modulo N. Okay. So one corollary to this this theorem is that if CA is congruent to CB modulo N and greatest common divisor of C and N is equals to 1, then A is congruent to B modulo N. Okay, A is congruent to B modulo N. So under this condition, cancellation, we can do the cancellation. Fine. So there is another corollary to it. Another corollary. This says that if CA is congruent to CB modulo P, where P is prime. P is a prime. P is a prime. And P doesn't divide C. P doesn't divide C, and P is a prime. P is a prime, and P does not divide C. It means that there is no factor. P is a not factor in C. Okay. मतलब P अगर डिवाइड नहीं करा तो C को अगर बड़ा नंबर है तो उसके फैक्टर में तो होगा नहीं. That is, they are going to be relatively prime. Okay. And then we can use the last corollary. Fine. Then A is congruent to B modulo P. So for sure, this is an application of the above corollary. Okay. So I don't think there is not much needed in proof. Anyway. Since P does not divide C, so P and C are relatively prime. Relatively primes. Okay. Relatively primes. That is the greatest common divisor of P and C equals to 1, and thus the result follows from the above corollary. Okay, fine. So we have done, I think, almost most properties of congruence relation, but let us conclude the discussion with a few notes. The first is the product of two integers, neither of which is congruent to 0. I think we have discussed or not, I don't know. That is 4 is not congruent to 0 modulo 12. Okay, this is not congruent to 0 modulo 12. And 3 is not congruent to 0 modulo 12. But 4 times 3 is congruent to 0 modulo 12. Okay, so even if they are incongruent, but their product may follow the congruence relation. Okay, and also the second one, this is somewhat you know, you have learned in integral domains. Okay, in integral domains where zero divisor and all, when you were reading it out in the last semester, I think in the third semester. Yes, in the third semester. So there you have learned the concept of zero divisors and all. Okay. So in integral domain, what we have seen that if the product of two elements is 0, then at least one of them is going to 0. Okay. So here 4 and 3 becomes zero divisors. Okay. But in case of integral domain, integral domains are those commutative ring with unity with no zero divisors. Okay. So this happens in a ring which is not integral domain. And the second thing, A is AB congruent to 0 modulo n, and such that A and n, greatest common divisor of A and n equals to 1. Then this implies that B has to be congruent to 0 modulo n. And this thing, you know that the product of two, because we are taking a and n, they are relatively prime. So of course, is non-zero we are considering here. So one that is another one has to be zero. So this happens in non-integral domain, and this happens in an integral domain. Okay. So if the product is zero, so one of them at least is going to be zero. And then the third one, in the third one, for prime p, for prime p, if a b is congruent to zero, modulo p, if AB congruent to 0 modulo P, then either A is congruent to 0 modulo P, or B is congruent to 0 modulo P.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.